This screencast will be about liquids and about the evaporation of liquids, so it'll also be about vapors. It's pretty easy, to some extent, to talk about solids because solids are made up of ions and atoms and particles that are in a very geometric arrangement. And when we talk about gases, those particles are so far apart that we can, in a sense, ignore the interactions between the particles when they collide. However, that's not the case when we talk about liquids. When we talk about liquids, these are the most difficult to describe precisely because you don't have an orderly arrangement and you don't have a purely random arrangement like you do with solids and with gases. And so you have to think about what's going on in terms of the interactions between those particles when they're so close together, but not in a geometrical pattern or arrangement. And that's where those intermolecular forces in the previous section come in. So you're very familiar, of course, with the words vaporization and condensation. So you would assume that when we talk about things going from the liquid state to the gas state, that whatever those values and processes might be, you would find them in reverse when you go from the gaseous state back into the liquid state. For example, that is going to be true with energies. When we talk about the energy necessary to go from the liquid state into the vapor state, that energy that's going to be released in the opposite direction in condensation ought to also be the same value. And of course, there's going to be a huge range of energies because you have a huge range of different kinds of molecules and atoms, from being nonpolar to being weakly polar to being very polar. And all of this is going to require different amounts of energies depending upon the strength of those intermolecular forces. So you're going to have a wide range of energies, as we've talked about before. Also, we're going to recognize that, as with gases, the average energy for the molecules in a liquid, again, depends only on the temperature. And as you might expect from previous discussions, if we were to graph this, we're going to find a curve, and that this should probably approach the x-axis, but you're going to have some particles down here that have very slow speeds, and some particles way up at this end that are going at very, very rapid speeds. We could say that this is the average kinetic energy along the x-axis, and this is the number of particles with those speeds in the liquid, or in the gas for that matter, that have those particular speeds. And you're going to have some maximum value here in the very middle, and you might remember this graph again from earlier in the chapter. But since you have a whole range of particles, you might have some particles that have enough energy, even when the outdoor temperature is cold, to evaporate and escape into the vapor state. Of course, as the temperature that the liquid is in gets warmer and warmer and warmer, more and more of your particles are going to have sufficient energy to break from their intermolecular forces of attraction between the particles in the liquid state and be able to evaporate. At some point, you reach a temperature of your liquid where all the particles basically have enough energy to escape into the vapor state, and that would be the boiling point. So if we look at this graph here, which is a much better graph than the one that I just drew, you can see that if you don't fall prey to thinking that temperature is along the y-axis, but temperature is really more a reflection of the x-axis, the average kinetic energy, and here's my number of particles that have that amount of energy, you can see that the temperature of the graph in blue is greater than the temperature of the graph that is in red, because its peak is farther to the right, not higher up. And as the temperature continues to get greater and greater, this graph is going to be stretched out more and more like that. And the peak, instead of here, it'll become there, and later it'll be there. But you should remember that the area underneath the curve in all three of these graphs the two that are part of the chapter and the one that I just drew here, the area under the graph, would represent all of the molecules or particles in that liquid at all of their energy values. And in all three cases, the area under the graph would be the same. The other thing you should notice, as we've mentioned before, that if this is some threshold of energy needed for a chemical reaction or needed to escape into the vapor state, at the low temperature, you have this many. At T2, you have even more particles that can now escape. And then if we look at a graph where I'll redraw this, now you have even more particles that have enough energy that can escape. Now, it's not a surprise to you, of course, that in order to go from the liquid state into the vapor state, you need to absorb energy. You have to heat it up. That would be an endothermic process. So we can talk about the molar enthalpy, or the molar heat of vaporization, as the amount of heat per mole of a particular liquid that is necessary to get that mole to go from the liquid state into the vapor state. And here we're using the letter H for heat. A lot of times you see in chemistry, but even more so in physics, we use the letter Q for heat, for the quantity of heat. So we can talk about the molar heat or the molar enthalpy of vaporization. Now you'll notice that little degree symbol there. The little degree symbol there is going to be pretty common in the chapters coming up as meaning under certain standard conditions. And we're going to find that the standard conditions for liquids and solids and things like that are not the same as the standard conditions for gases. They might have the same standard pressure, but the standard temperature for gases we usually take as being 0 degrees Celsius, which is 273 Kelvin. But when we talk about standard temperature, in this case, like the molar enthalpy of vaporization, we usually use room temperature, which in most books is 25 degrees, though on some books I've seen 20 degrees as the standard temperature. And of course, your molar enthalpy will be different depending upon which one of these temperatures you're using as your standard. And of course, going from the vapor state back to the liquid state, in other words, recondensing, is the reverse, and that's going to be exothermic. If it takes heat to go from liquid to vapor, there's going to be a release of heat to go from the vapor back to a liquid. And in fact, in Florida, if they're expecting a cold spell that might threaten or freeze their citrus crops, what they'll often do is spray water vapor into the air, and as the water vapor condenses back into a liquid, it releases heat, and then when the liquid freezes into ice, even if the ice covers the tree and the fruit, it releases more heat. So as long as the cold spell doesn't last for more than a couple of days, the exothermic release of heat as the water goes from vapor to liquid to solid helps to preserve the fruit and the trees just long enough until the weather returns to a more normal temperature. So if we look at these charts right here, we could begin to say, well, what are the trends that we see? For example, if we look up here, there's our halogens, fluorine, chlorine, bromine, iodide. And you can see, of course, the molar masses are getting bigger. And as the molar masses get bigger, you can see that my heat of vaporization begins to get smaller. Part of that, of course, is because the polarity of these molecules is getting weaker and weaker. Hydrogen fluoride is going to be much more polar than hydrogen iodide because the iodine, its electrons are way much farther apart, farther away from the nucleus than before. And you can also see your boiling points here change as well, from very high for hydrogen fluoride to even positive, and then it goes negative again. We can also try to look at molar masses. Look how my molar masses are getting big here. Notice that my heat molar heat of enthalpy of vaporization increases. And here, if these molecules are all nonpolar, then you've got your London forces, your dispersion interaction forces, become more and more significant the bigger the atoms are, because you have more and more electrons that might find themselves more on one side of the molecule than on the other side. And so as a result, it's going to take more and more energy in order to go from the liquid to vapor state, which means your boiling point is going to get higher and higher. You see that same trend as we go down the periodic table with the inert gases. Molar masses go up, and therefore the molar heat, molar enthalpy of vaporization is going to go up, and therefore your boiling point is going to go up as well. And not to belabor the issue, but as we look at the diatomic elements, the Brinkerhoffs, and arrange them in order so that the molar masses are going up, so does the enthalpy of vaporization go up, and so does the boiling point go up. All right, let's take a look at this problem right here real quickly. If we put 925 milliliters of water, almost a liter of water, in a pan at 100 degrees Celsius, and the water slowly evaporates, how much energy is transferred as heat to vaporize all of that water? And it's a pretty simple dimensional analysis problem where we take our milliliters and convert it into grams. For this particular liquid, it's pretty close to 1, and then we find our number of moles from grams. And once we get my moles of water, then we can multiply my moles of water by the enthalpy per mole, so moles cancel out, and there's our amount of heat. Let's talk about vapor pressure a little bit. And before I do that, I wanted to mention something right here. And that is that if enough water condenses from the air to fall as an inch of rain on an acre of ground, look at the huge amount of energy. And notice that it's in kilojoules. So basically, we're talking about 0.2 billion kilojoules of energy being released. And the text says this is equivalent to about 50 tons of dynamite, or the energy released by a very small bomb. You might also have experienced in the wintertime when the snow starts to fall. Sometimes the temperature seems to go up a little bit than it was before because of the liquid turning into snowflakes, and there's a bit of release of heat energy, and that changes the temperature just a smidge. All right, let's talk about vapor pressure. So if I have a container over here, let me draw it, and in that container we have some liquid. Some of the molecules on the surface of this liquid are going to be able to escape into the vapor state. And the other molecules that make up the liquid will not have enough energy to escape. Even at a relatively low temperature, even in a cold day, you're going to have a few molecules of that liquid that will have enough energy to escape. Once again, remember the curve that looks like this. Most of your molecules won't have enough energy to escape, but you will have a few that'll have enough energy to break free from the surface tension of the liquid and escape into the vapor state. Now, if we put a cap on this, let me fix the drawing. If we put a roof over the top, now we're going to see that some of these particles that have evaporated, eventually there are going to be so many particles that have evaporated into the space above the liquid that some of them are going to begin to condense and go back into the vapor state. And at that point, we reach something that we call a dynamic equilibrium. The word dynamic, of course, means it's going in both directions at the same time. Or over here, we could say it's going from liquid to vapor. At the same time, it's going from vapor to liquid. We should also say that this is a physical equilibrium. It's not a chemical equilibrium. And we're going to be talking about chemical equilibrium a lot more come February. Chemical equilibrium is when the rate in which reactants turn into products equals the rate in which those products revert back into their reactants. We need to make a couple of comments here that we are not saying that the mass of liquid equals the mass of vapor. We are not saying that at all. What we are saying is that once you reach equilibrium, whatever the mass of the liquid is not going to change. And whatever the mass of the vapor is not going to change, even though you have molecules of liquid becoming vapor and molecules of vapor going back to liquid. Their individual masses don't change. And hopefully that makes sense. And here's a diagram at the very bottom of the page that says, imagine that we put a volatile liquid down here in our flask, and you might have done a lab where you have a volatile liquid that you allow to evaporate in a container, maybe a syringe or something, and or into an Erlenmeyer flask. And as this liquid begins to go into the vapor state, eventually you're going to reach a point where as much of it, more and more of it evaporates. You might still have a little bit left, but at some point, the vapor pressure pushing down on this column of mercury equals this pressure right there. Remember, pressure is going to be force per unit area. Area is going to be the cross-sectional area of that capillary tube. And the force is going to be the force of weight of this mercury that's in the tube. So when this pressure of the mercury pushes down and it's equal opposite to the vapor pressure on the other side of the U-tube pushing down, now you've reached equilibrium. And now no more of this liquid is going to evaporate. Now, to be technically correct, some of it will evaporate, but you're going to be in equilibrium, so some of the evaporated stuff will go back into the liquid, and the amount there will stay constant. So this is a physical dynamic equilibrium. When we look at three different liquids, we have diethyl ether, and if you look at this particular molecule, there might be an ever so slight polarity perhaps, but not much, because it's pretty much the same on the left side of the molecule as on the right side of the molecule. So this molecule is pretty close to being nonpolar. Then you've got ethanol with your hydroxyl group over there and your oxygens, and this is certainly not a symmetrical molecule, so this molecule is going to be polar. And then you have the good old water molecule, and this molecule is very polar. In fact, we would say that we expect there to be hydrogen bonding here. And the point being, of course, that these molecules for water are going to be much more tightly held together than for ethanol, which will be much more tightly held together than diethyl ether. I have a textbook in earth science that uses the word stickiness for polar molecules sort of sticking together, where their intermolecular forces are substantial. And you would expect, therefore, that the normal boiling point for diethyl ether is going to be lower because it doesn't take that much energy to separate this molecule from another one. And the normal boiling point for ethanol is going to be higher because it's going to take a little bit more energy to separate this molecule from another ethanol molecule, because those molecules are very polar. And it's going to take even more energy, and therefore you're going to have a higher boiling point for water, because it's going to these molecules have that hydrogen bonding and very strong dipole-dipole interactions, and it's going to take even more energy to separate them so they can go into the vapor state. Another thing that we should point out here is that that on the left side of the curve, for example, this side of the curve, these are going to be liquids, and on the right side of the curve, you're going to have a gas. Or over here, this is going to be liquid ethanol, and on the right side is going to be vapor or gaseous ethanol. And the same is going to be true here and here. That's what's talked about right up here. And you would expect, of course, that as you go from cold temperatures up to high temperatures, that the gases are going to be on the right side and the liquids are going to be on the left side. Now here you're going to have pressure, and of course the more pressure you put on the liquid, it's going to take a higher and higher temperature. You're going to have to go farther to the right in order to enable those molecules to separate enough to leave the liquid state to become a vapor because of the pressure that's pushing down on it. It's keeping it from trying to go into the vapor state. The other thing we need to point out about these graphs is that along the line of the graph, if you have a pressure temperature of a particular molecule, in this case of water, that falls on this line, that's where it can be either the liquid or the gas, because you're at equilibrium at that combination. Again, notice that there are going to be no net change in the masses of the two phases. And again, remember, we're not saying that the mass of the liquid equals the mass of the gas. What we're saying is that at equilibrium, even though molecules are going from liquid to gas and gas to liquid, the mass of the gas doesn't change, and whatever the mass of the liquid is, it doesn't change either. And the pressure of that vapor that has escaped is called the equilibrium vapor pressure, which would be inside a closed container, or in the case of water vapor, whatever the equilibrium state for the water vapor pressure is in a room. And you might have seen a chart of water vapor pressures, because there's always going to be water vapor in the atmosphere. Even in a desert climate, it's going to be very, very, very small, even perhaps almost zero. But at any temperature, there is a specific or unique water vapor pressure. The word volatility, good vocabulary word, points out the fact that some liquids are way more volatile than others. Water, we would say, is not all that volatile because those strong hydrogen bonds help to hold the water molecules or stick the water molecules together, resisting the water molecules from getting far enough apart that they escape into the vapor state. But if you have a nonpolar liquid, let's say gasoline or acetone, those liquids evaporate very, very easily. And so they would also be very, very volatile. So you never want to store volatile liquids. You never want to store volatile liquids in a small area, even the size of a garage with the door closed, because the volatile liquids could accumulate, at which point a spark could ignite them, and that, of course, could cause an awful lot of damage or be harmful if somebody is in the area. Right here, at a higher temperature, more molecules have enough energy to escape the surface of the liquid. So you will have evaporation even at cold temperatures. And then finally, all points along the vapor pressure versus temperature curves represent conditions of pressure and temperature at which the liquid and vapor are at equilibrium. We mentioned that already. Here's an interesting problem. You place 2 liters of water in an open container in your dormitory room. This is a college chemistry textbook, after all. And the room has an amount of this many liters of air in the room. So you seal the room, which I would recommend you not do, especially because you probably aren't going to do your laundry more than once a month, whether you need to or not, or else you'll keep the dirty laundry in your room until you can go home and have your mom do it. But you seal the room and you wait for the water to evaporate. This, by the way, again, is not how you wash your clothes in college. Will all the water evaporate at 25 degrees? The density of the water is almost 1, and if you went on a chart, and they have charts in college, you can always go online, of course, and at 25 degrees, if you look it up, at 25 degrees, the water vapor pressure is 23.8 millimeters of mercury. So the way to do this is to calculate the amount of liquid water that must evaporate for the vapor pressure to exert a pressure of 23.8 millimeters of mercury. Once you reach that vapor pressure, no more net evaporation is going to take place. So when we do the problem, first thing we want to do is decide what value of my constant do we want to use. Your textbook has decided to use this constant, which is in atmospheres, so therefore it requires the conversion of millimeters of mercury into atmospheres of pressure. And that's the number then that comes in here for pressure. This is the volume of your room. This is the temperature of your room. And here you find your moles of gas. Then once you find your moles of gas, you're going to convert it into grams. So moles cancel. And this gives you the grams of water that you would have in the air at a pressure, water vapor pressure of 23.8 millimeters of mercury. And when you convert that many grams of water into milliliters, that's 983 milliliters of water. So basically, that's how much of your water would evaporate, which is only about half of the available water that needs to evaporate to achieve the equilibrium water vapor pressure, so it would all evaporate. Now there is an equation that can be used to calculate your vapor pressure, but I'm going to stop the screencast at this point and pick up on vapor pressure and the very important Clausius-Clapeyron equation later.